Hi everyone, Nick Russo again, and this is the final video in our series. We're going to do another walkthrough of a complexity assessment I wrote, again, another original research paper. This time it's on OSPF over hub-spoke networks, trying to make that scalable over WAN, basically. So think about, to use some Cisco terms like OSPF over DMVPN. How can we do this in a way that's both scalable and has some high availability or HA built in? So we'll kind of skim through. I'll give you a technology overview without getting too much into it, because I want to, I need to give you an understanding of what we're even doing, but not read the whole paper to you, basically. So if we want to look at just the basic DMVPN deployment, suppose that I have some kind of carrier network with, in this case, R11, R9, and R13. I just have some kind of transport, internet, or MPLS, or whatever. I have a spoke, and then I have some kind of hub. What I do at all the hubs is I have a loopback that's the tunnel source, so not the connected interface. That loopback is an anycast address that is configured on multiple different hubs in the network. We advertise that to the carrier using BGP, and then my spoke is going to go towards the closest hub. So it's really straightforward. R13 basically is going to choose which hub the spoke sends traffic to based on its BGP best path. So if we look at a few other diagrams with multiple hubs, it becomes a little more apparent on how this solution works. So here's an example. Again, a little bit of a complicated diagram, but ignore all the text. I've got two hubs, R2 and R3. R5 chooses R2 as the closest hub, which is clear based on the diagram, assuming all the links have the same cost. And R6 chooses R3 as the closest hub, again, assuming shortest path across the diagram. If R2 suddenly fails, then R5 will tear down its tunnel and rebuild it with R3. Yes, there will be an outage there, but that stateless failover is what's going to allow this technology to work. The scalability of the solution, which I kind of glazed over, but I'll describe it briefly, is that we've configured OSPF at the hubs not to advertise any of the hub subnets back down to the spokes. So effectively, the hub is saying, I'm not going to advertise any LSAs down to spokes. So number one, as I said a couple seconds ago, none of the hub networks are sent down to spokes. But even better, the spokes don't learn information from one another either. So the spokes can scale much, much better. They just have a static default route that points up to the tunnel, and then the hub will learn OSPF specifics for all the spokes. This is equivalent to just doing hub level summarization with EIGRP or BGP. The only difference is that because OSPF, based on its nature, can't do that in a fully dynamic way, we basically say, hey, the hub is not going to send any information to the spokes. He's going to leave them blind. But then I'm just going to put one static route on every spoke pointing up to the tunnel head end. Pretty clear. We've used this in production. I've used it for IPv4 and v6. It works very well. The failover is pretty fast. You can typically tune the timers to be around 45 seconds to a minute. All that's detailed in the paper. So now you understand the basic solution. So let's look at the complexity assessment, which is why we're here. So I'm going to skip all the fun failover stuff and the timers and the testing, and let's get down to business. So it looks familiar. It looks just like the other document. I try to be consistent. So here I'm saying I give my little background on a complexity assessment, what the book reference is, and how this section is written. For state, again, I give my description, the amount of control plane data present, and the rate at which state changes. So we care about the quantity of state and the speed of state. So the first claim that I make is that the state retained at the hubs scales linearly as spokes are added. That makes sense because let's say each spoke adds 4 routes. So every spoke has a data VLAN, a management VLAN, a voice VLAN, and a spare. Let's just say that's how it's set up. Every time I add a spoke, the hub is going to learn those 4 routes. Let's assume there's no summarization there. So every time I add a spoke, it's a linear scaling. Add 1 spoke, get 4 new routes. Add 10 new spokes, get 40 new routes, etc. Okay, so that's clear. That's the total state in the network. That means that from the hub's perspective, he has a linear scale of state increasing. Now, the state retained at the hubs, or should I say the state retained at the spokes, because we just talked about the hubs. We know the hubs are linear. The state at the spokes stays constant. Whether I have 10 spokes or 10,000 spokes, they only have their local connected subnets. So they got those 4 connected routes plus the tunnel plus a default. So the spokes basically scale in constant time no impact on the number of spokes added. This is the main selling point of this design, where you need a very large scale OSPF network, either because you have a lot of nodes, for example, high quantity of spokes, or a very high churn. So I've deployed this in environments that have many hundreds of spokes, which is a pretty reasonable number. I wouldn't call it huge, but it's large enough. But those nodes join and leave the network very regularly. So now you can kind of see the quantity of state is pretty high, and the speed of state, the churn, that's high too. So we can clearly see that by doing the OSPF LSA filtering at the hub with the static route at the spokes to simulate kind of distance vector based hub summarization, we can achieve really great scale because we've really throttled the state way down by doing that. I talk about regions here. I don't want to get too much into this assessment on regions, but effectively what I was talking about earlier in the document is that we can regionalize our hubs using some BGP manipulations and determine where our spokes connect to give us a little bit of control over how the network works. But in general, this last statement here, I think, really solidifies the point I'm trying to make, is that the routing state on spokes scales in constant space and time as spokes are added. Again, a fancy way of saying you can add tons and tons of spokes as long as your hub can support it. Now, in terms of optimization, again, I'm using the positive connotation word here. And in this case, we are trying to see what impact do you think this design is going to have on our forwarding? Now, there's a big optimization trade-off, and I'm writing this in the second paragraph, so I'm kind of jumping down into the second paragraph because I think it's highly relevant to mention this up front, is the downtime. So I said this was a high availability design, and it is, but the availability is lower than if you just had 2 OSPF hubs in the network in the first place, because then you could just tune your OSPF timers or maybe use BFD, depending on the technology, to get faster failover without needing to have BGP converge, then set up new tunnels, and then do IPsec again, and then form OSPF again, etc. So it is going to be a little bit slower converging than if you had 2 hubs, but it's going to be massively scaling. Trying to scale OSPF with 2 hubs is very hard because that LSA filter technique I just described doesn't work so well. But by breaking up those hubs into 2, even though it's the same mesh and they have the same config, breaking them up into what appear to be different Anycast meshes, we achieve good availability, just not excellent. So if our optimization metric here is high availability, we may lose that. We may also have optimization problems if there are multiple overlays. So if I have multiple different overlays and I have just a static route that points out of tunnel 1, well, what about tunnel 2? I can't learn any dynamic routes. So I might need to have some static route management with some longer matches that go one way. You can quickly see how this would get out of control if you had multiple meshes to manage. This design is really well suited for single mesh, 1 hub at a time type environments. So again, not the answer for every WAN environment, and I am absolutely not suggesting that OSPF is the right protocol to run on your hub-spoke WANs. I'm only saying that if you're forced to do it for some reason beyond your control, here is a a good performing solution that I wanted to document and share. Last, let's take a look at surface interactions and how tightly intertwined these things are. Again, I use this term minimally deep, not sure why. I'm really saying that this is a shallow interaction. I've got front door VRFs to separate control planes. Again, these are just minor implementation details. I don't want to get too much into that. You may have a spoke site that is running some other IGP. For example, I've got OSPF process 1 up to the hub, and then maybe I've got OSPF process 2 that runs down to my layer 3 firewall or layer 3 switch. So I may need to do some redistribution there. But remember, I wouldn't consider that deep. That might be something that we consider wide. So if I have 100 branches and they're each running multiple OSPF processes, doing a little bit of basic redistribution with their connected layer 3 switch, there's really not a possibility of loops there because it's just little stubby networks being redistributed. Okay, no big deal, whatever. The depth of that interaction is very shallow because, again, you're just redistributing a few routes, but the width, or the breadth, I should say, is very wide because you're doing it at potentially all your sites, depending on where you're doing a technique like that. That's why I'm making the claim this next paragraph, basically the words I just said, is relatively deep and very wide. So when we talk about timer tuning selection, again, not terribly deep. We do have to coordinate between a few different timers, but the dependencies typically aren't too bad. But I do need to do that coordination everywhere. All the different nodes need to have that same configuration between the different timers for DMVPN, IPsec, OSPF, etc. if you're using DMVPN. This would work for a variety of different hub spoke technologies. I just chose DMVPN because that's what we use in production. So this design is, and this is more of just kind of a comment at the end, is the width of the interactions. Even though we're talking about depth and breadth, there's also kind of a consistency factor. Is with the BGP traffic engineering solution, we didn't have a lot of consistency because at any given time, the amount of state could change, and the amount of surface interactions may even change depending on which way the flows are going and how we decide to evaluate that. But in this design, we don't really have that problem. It's a little bit more consistent. We know that every time we add a spoke, what the state's going to be, what the traffic flow is going to be, and what the surface interaction is going to be. So the design, I say it here, the design does not encourage one-off modifications like a hub that doesn't use eBGP, that only uses connected routes. So some may see this as a benefit where one-offs just don't work and you end up with a nice clean network that has consistent surface interactions everywhere. Because again, one-offs, we all understand how hard one-offs can be to manage sometimes. Some people may see this as a bad thing because they want extra customization. So that is the end of the second assessment. And just to scroll back up, this was only 2 pages long, just like the first one. I would recommend that you do a few of these on your own for maybe some of your favorite designs. If you've done a design in the past, maybe pull up the design document you wrote and give this a shot. Spend a few hours, see if you can write a complexity assessment, and then roll this into your daily work. That's what I would recommend you try. So this is the end of the looking at some live assessments. We'll do a closing thoughts video next. So I look forward to sharing some final words of wisdom with you. Thank you.